Can you hear me? Sounds good, all right. Welcome to the seminar on building things with distance functions. We will not talk about how to render the distance functions, and we will also not talk about how to apply materials or anything, because both are interesting topics as well, but each would fill an hour in itself, and I'd like to just focus on the geometry building thing. So we'll start by it seems to work, right? By the basics. This I'll like this. So here we have a distance function. It's the one I've written here. You see a visualization on the left. You see the object itself, it's a sphere, and you see the distance from the sphere on the ground plane visualized in like lines of equal distance. The distance function itself works like this. You input any point in 3 space, call it p, and you return a float that is the distance from that point to the nearest point of geometry in the whole scene. So in the case of a sphere, we center the sphere at the origin of the coordinate system in this case, and we take the distance to that, and we subtract something, which is the radius of the sphere, and then we get a distance. So spheres are obviously not very interesting. And if you sit down with a piece of paper and you think, well, okay, sphere, I got that. How can I make this into a box, for example? You can come up with a formula for a box. It takes some thinking, but you can manage. And in any case, there's for many primitive objects, there's a lot of information on the internet. Like on Poet, there's the ray marching toolbox thread, which has many examples, and elsewhere on the net and on Shader Toy, you'll find many examples. So we won't spend the whole time like building boxes and other primitive objects, but I'll show you the functions. So I have this so I have this section in our library that we include everywhere. There's just you can see the box here is not that long if you think about it, not that interesting. So and when we build things, we don't use that many of those primitive objects as you might think. So normally we just use like boxes and planes, and that's basically it, and the rest is just by manipulating space. So, and I'll show you in a minute what I mean by that. But one classic thing is repeating space by using the modulus operation. So I can do it. I can show you another thing first. If I manipulate p in this way, something changes. Or to make it a bit more visible, sphere is now floating. So you notice I've written -1 and it's gone up. So the coordinate system is y is up. I've subtracted 1, so this seems a bit counterintuitive, and it will be like things will seem reversed all the time. That is normal. That is it's not you, because the thing is we are moving space down by 1, which moves the sphere up by 1, which is the same. So you have to get used to this kind of thinking, like in reverse. You're not translating the sphere, you're translating the space. That makes the sphere go up. So now that we know how to translate things, we can do, for example, things like this. So if I do it like this, bad things will happen. I'll show you. So what just happened? I replaced the x-coordinate by the modulus of the x-coordinate by 5. So it means it will go from 0 to 5, from 0 to 5, and so on. And that means at 0, there's it will intersect the origin, and our sphere is broken now, and you get these discontinuities in the distance function, which is anyway totally bad. You can see here artifacts because the rendering will, of course, use the higher distance estimation here, where it's wide, and will step into the object, and yeah. So the good method to do this is do it like this. So for the original sphere, nothing changes. You add half your length, and you subtract it afterwards, and everything's fine, and you get an infinite amount of those spheres, but you've only written 2 lines of code. So you don't have to write a loop to get multiple objects, and that's probably the biggest lesson anyway. If you want more than one of a thing, if you write a loop, you're doing it wrong. It's almost always possible to repeat space in some clever way, so you don't have to execute a statement multiple times, because imagine that this would be a more costly function. This would be a complicated object, and you wanted 3 of those, and then you write a for loop, and everything slows down, and yeah. So you'd always try to repeat space in this way. So the thing is, things like this, if you write them into the code, there's 3 numbers in them. Those 3, after 2 days, you won't know what they mean, and then it's 3 hours before the deadline or after the deadline, and you're editing things, and you're editing like, oh, I want to increase the space, and you're only changing 1 number, and yeah, then everything's broken again. So what we did, we took those things that you often use and made them into what we call operators. So instead we just write this. So I can show you the function in the code in the library. So there's the function. It's exactly what we've written before, except that it does 2 things. It manipulates p in place, which might seem counterintuitive, but does make sense. The second thing is it returns an index for the repetition cell that you're in, that you can optionally use if you want, and you can use it as a seed for your random number generator and use it to make some variation within the cells. And we have made many of those functions, and you can just scroll through them, and there's a lot of stuff. I'll show you one obvious other one. So there's the one for 2 dimensions. All right, you've seen things like this all over the place. It's basically what everybody's doing, but I can really, really recommend using this kind of operator thing to make it more readable, because it just says repeat space in 2 dimensions, and I mean these two, and those are the sizes of the rectangular grid cells. So it makes the code more readable, and also, yeah, if you're going for a size, more compact as well, probably. So, yeah, we'll come back to this kind of thing later. The second thing is, okay, I want a bit more interesting objects, and we'll start by combining 2 objects, and we'll see what we can get by combining two different objects that we evaluate individually. So I'll make a box. Oh, and by the way, if you have any questions, please at any time just ask. That would be totally fine with me, because yeah, well, okay. So make another box. Okay, the usual thing is to combine them this way with a minimum operation, and so this is what happens. If you think about it, if you take 2 distances to 2 objects, so we have distance to the object 1, distance to object 2 in those 2 variables, and we take the minimum of those, that means we just look at the object that's closer to us. And as soon as the other object becomes closer, we only look at this. So we're looking at the, so it's a Boolean operation. We're looking at the union of these 2 objects. Yeah, the obvious question is, what happens if we use the maximum? We get the intersection of those. Okay, all right. So far, that's probably what everybody's doing. But the thing is, if you look at situations like this, where 2 objects meet in a orthogonal way, so you have one direction to the right, which is distance from the right object. Then you have another direction going up, which is the distance to the object on top. And you can, if you want, use that as a coordinate system in 2D. So I've like those 2 numbers that here in the ground plane, they form a coordinate system, and I'll show you what you can do with that. So we now have a rounded edge here. I can make it a little bit bigger. So what this thing does is it interprets the 2 distances you give it as a coordinate system in 2D, then evaluates another distance function just in 2D, in 2 space, and computes the distance to a quarter circle of radius 0.7 in this case, and outputs that. And outside of a small volume, it changes nothing. So the rest of the function is not modified. So I'll show you. So there's many flavors of that as well. So this is what it looks like. Yeah, it looks, if it's inside the interesting area, so that would be this little square thing. Then it returns the distance to the quarter circle. So I don't want to go into detail. You can take a piece of paper and think about that if you want, but the basic idea is take the two distances, make it a coordinate system, and then inside that coordinate system evaluate anything. So what you can do, for example, would be this. This would make a nice 45-degree intersection thing. I can show you without the ground plane. So if we combine objects this way, we instantly get like added detail for a very low price, because this example might not be that interesting, but well, once you start adding objects and using those operators in the right places, you can get a very convincing, very natural look, because all the little details just seem to be right, and you'd never model them explicitly. So you just get a lot for free. I'll show you some more examples. I've made one. I made that just I think 3 days ago. That. Just, yeah, well, make some stairs. Okay. I think I'll rotate. I want it. Oh, no. Okay. Let's just scroll a bit more. Yeah, I can just show you what happens in the analog for the maximum. So I just this one again. So we get intersection of those, and this thing can become a bit problematic. So at this point it looks nice, distance looks good, but if you stack those operators, you might violate the assumption that the intersections are at right angles. So it works good at 90 degrees, it still works somewhat at 60 degrees, but then it tends to break down. And of course, if you stack those inside each other, you have to be careful. So there's always a thing to look out for. Yeah, then we could use the divide operator, which is like subtract one of those boxes from the other. Then we get this. So yeah, it does look more interesting than two boxes already, because you get all those little edges and everything just looks more complex than it actually is. So okay, so I've done this talk before 2 weeks ago, and this is now the hungover edition. So I'm probably not that fast at the moment, and I'll just cheat by looking up there what I just produced. All right, yeah, we can look at this one. That is nice. Okay, we'll try to build some geometry to make it from those trivial examples, to make it a little bit more interesting. So I have this version of the box, which just takes 2 dimensions. So in the other dimension, it's an endless box. So So, like this. And then we'll try to make some windows into the wall. So the wall goes in X direction. The window should be bigger than the wall to be able to actually cut it. So maybe double the width. It should be not as high as the wall itself, and in the direction, well, maybe like this. Oh yeah, I'll just show you in a minute what that means. So, what did I do wrong? Ah, right. Cool, thanks. Right, well. Okay, so we've cut a hole in it, and I've used this operator thing which makes those little columns, I think. So it's just the same thing that you've seen before. It's like basically like this one, but a bit more interesting. So this one can just take an arbitrary number of those things, and just you can, if you adjust it in the right way, you can make more or less convincing. No, it's not too bad. All right. So this is what we got by cutting out a hole. So we will repeat the window now because we want more than one. So that thing goes in Z direction. So let's say so now a lot of windows. Then we'll increase the height of the wall a bit, and then let's say want to make the window a bit more interesting, so we will add something to it. And let's say, so Z direction is the wall, so all right, let's just see what happens. Now happens probably nothing. Oh, it doesn't. Oh no. So what I just did is, I'll show you in a minute. So I'll just put a big number in. So I made this circle. So at the moment this doesn't change anything, but I'll move it a little bit. We've learned how to do that. Height of the window is 4, so I'll move it up by 4. So we get this arch thing. So, and you notice all those, this is totally seamless, and it looks like you actually modeled it, which, yeah, but it said you just arrived at the party place and started coding, and you already have some things going on. You can always, at any point in time, visualize what else you're doing. So this is our window. This is what we're cutting from the wall. So what it looks like outside is totally irrelevant, as long as the place where it cuts the hole from the wall is the right shape. So we'll make it a little more interesting again. So now nothing will happen because I've just mirrored the z-coordinate, but the scene was already symmetric, so nothing happens. But if I now move the scene a little bit, we'll see what we get. Okay, this would be one possibility, but it looks ugly. So we'll do it the other way and maybe like this. So we've just mirrored the whole scene, and again, if you want to visualize the object that we've cut out, now it looks like this has this sharp edge at the top. All right, so we've got this window like this, and then let's say we want two of them, we want them in pairs. So we'll just do the whole thing again and do it like this. A little bit too much. Still too much. So, all right. Like, yeah, looks all right already. Okay. Yeah, and if you remember our 64K from last year, the timeless, this is exactly what the church windows were. This is probably very close to the actual code. There was a third thing inset over there between the two, but this is basically it. But now we want to build the rest of the building, and obviously we have a wall. Now we need the roof, and then we are almost done. So for the roof, we'll use another endless box. By the way, how late is it? So I'll just copy it from here. So we just start by making the roof a flat one. So it will go like, will be somewhat big and will not be very high. So like this. So now the roof is somewhat in the wrong place, so we will move it. So now we get into a thing that it's quite common. We've manipulated our this value to make the circle that we use for the window, and that is why the roof is now appearing in the middle of the circle. So if I use that to raise it again, and then I want to change where the window thing is, I'll change where the roof is. So you can think about this as like nesting coordinate systems. You're always manipulating this coordinate system that you have, somewhat more. In this case, we've mirrored it, we've moved it. The mirroring is insignificant for the roof that you want to build, because it will be the same at every z-coordinate anyway. But what I normally do is I keep a copy of the original P, and I give it some name. So yeah. So the first one could be named like this, but maybe somewhat more inside. Maybe inside if I wanted to do some things inside the window, give them some structure or some detail, I'd call it maybe a window P, and then use that and have an actual name, and not have a real big mess of code and change one number here and then everything else moves as well. So it really helps to give things names that maybe your group members or yourself the next day might find helpful. So do it like this. Right. So it will move down a little bit, and now we can manipulate this without any fear of breaking anything. Code gets a little bit bigger, I give you that, but you can always crunch this when you're size optimizing, if that is your thing, afterwards, when you know what you're doing, because modeling this is always the experimentation and everything is flowing, and then you find a nice effect and you do something, and then you do that instead. And so size optimization is for later. And also, you don't have to use like one-letter variable names as we used to do in the past, because there's tools like shader minifier, or you can always roll your own to replace the variable names with shorter ones. So there's really no need to use obscure names. Just write it out. Just give things real names like roof or wall or whatever. Just call it what it is. So I could have made a variable which said my wall is this high. I didn't, so I'll do it like this, which might be bad. Oh well. And so, okay, quite ugly, but it might work. So maybe I'll make this little edge. Then we'll rotate it. I haven't shown you how to rotate things. That is something that we could rename maybe. At the moment we write it like this. I should use the correct one. I'll show you the code in a moment. All right. Why is that? Right. Okay, wrong direction, but it works somewhat. Okay, yeah, we'll fix it in a minute. If I actually paste it. Okay, cool, we've made some roof. All right, so the code for this, at the moment we write this as this macro. It probably you could use a function, but I don't know. Maybe the macro, well, more or less for historic reasons, but yeah, maybe we should give it a better name like this to make it sound like the other ones. In any case, yeah, you can rotate things, and building is almost complete. Now we just need another side for it. So we already know how to do it. We mirror space. We've done it with the windows, so we'll do it again. So all right. So I have to do it like this, and maybe I'll just that. So that's better. And then we'll just mirror space again. So we'll try to make the building complete by making another side. So this should be the x-axis. We'll just see what happens if I don't add anything. So, all right. It looks like a bus stop or something. So we'll just invert it, so we get the other direction. Then we see, yeah, well, this is a very small building. There's no space between the walls. So we'll just move it by some amount. I have no idea if the sign is correct. Normally it isn't. So, yeah. But anyway, okay, so we made this hallway thing. So, yeah, well, we're almost done. it is technically a building now. And then we really can go crazy from this point, because we have a correct distance function for the whole thing, because mirroring, which is all we did, and repeating space if the objects inside are placed, okay, I'll come to that later again, still gives you a correct distance function. So you can just look at it, and that is, yeah, it's still somewhat correct distance function. And if you keep the invariant of the distance function being an actual distance function, that means you can stack those operations all over the place. You can really go crazy, and it will not break. And so the important thing is what mathematicians call Lipschitz continuity. It means that when you, from one point in the distance function, you move towards the surface, the distance, and you move by 1 unit, the distance function should change by 1 unit as well. It sounds like somewhat self-evident, because like going by distance 1, then you've gone 1. But the thing is, if you visualize the whole thing as a 2D height map maybe, and with the distance the height, then means that the slope must not be steeper than 1. So because if it is, your rendering will skip things, and you will get artifacts, and you will have to multiply everything by 0.7 or something to make the slope a little bit less steep again, but then it will be slow. And just don't go there. Don't multiply by any values, and just keep the Lipschitz continuity. So I think a way to visualize this is you can look at the magnitude of the gradient of the function. That means you compute the normal. You do that by sampling the distance field in 6 locations that are very close by the pixel that you want to compute the normal of. And then you take those 6 distances, take the differences, and then you get the normal. It's a normal thing, what everybody does. But you can also look at the length of the normal that you just got. Because if your distance function is perfect, it will be 1. So I've just visualized the error of that length. So black is 1, so black is good. So you see some lines where it's green. The blue thing is iteration count, so it's something different. And you see it that at some places it's a bit green. That's because the normal has significant length at those places, so the edges will have, because the kernel for computing normal will have a finite size, so you'll get some value at the edges, but you can just look at the length of your normal to see if your distance function is broken. So it should be 1, and I really encourage you to make a visualization like this. In my case, I did something like if the distance is too big, it's red. If the distance is too small, it's green, so you can see which way is wrong. And red is also the indication for the worst thing, because if the distance estimation is red is a too small distance. If the distance is too small, the other way. If the distance is too big, your ray marcher, if you're using sphere tracing, will step inside the objects and everything will break down. So you really want to see that up front, and not only when you're positioning the camera and have to avoid the artifacts and so on. All right, I've gotten carried away somewhat. I'll just throw in some other operators. I don't think I have time to explain them all, but you get the idea. It's all the same stuff. So I'll just use this one, for example. And we'll see what happens. Okay, so we've repeated space in this way, and then maybe we can, let's just go totally crazy. Do it like this, rotate, there's a T missing. Rotate by some value, then do it again with, like, I have no idea what I'm doing. Maybe do it like this. So we'll just look at what happens. Okay, now we got this. I couldn't have predicted this, so whatever. But you get the idea. So you get some accidental things which you might want or maybe not, but maybe this is what you wanted. I have no idea. And you've just seen we've made this interesting thing, and your 4K procedural graphics is done. So you still have to do some shading and so on, but in the end, the geometry part of it can be really, really fast if you build yourself a set of tools that mainly consists of operators that manipulate space in a consistent way. If you use that operators to introduce some variation, which we didn't, put different tiles in each window, for example, so you don't repeat the same pattern inside and so on. And also the thing about the combination operators for intersection and other Boolean operations is just incredibly helpful and and convenient. So I haven't talked about half the stuff I wanted to talk about, but how's the time? 13 minutes, including questions? Including questions. Okay, all right. I'll just show off some more things and have a look at the code now. You might so we're inside that. So all right. So you might remember this from last year. So the city will build that exactly the same way. So it's the code is somewhat right. The ground plane is in the wrong place, whatever. So the buildings extend down there. So you have to do it like this. So there's just one building because we don't write for loops. I'll just open the file. So this code is really messy and really old, and I don't want to look at it really hard because it might break. But we'll just comment out random things and we'll see what happens, and it might help understand what's going on. So the beginning is just the same what I just showed you. Basically with bit different flavor. So if I comment out this one thing, we get this. So layout is less interesting, of course, but buildings are still somewhat different. So the real interesting part happens if I comment out this part, and then you will instantly get it. So now it looks like this. It is a bit broken, but this is what the whole city is. It's just one big facade. So the city is just one house, and we just vary some parameters for to make the variation between the buildings. And if you look at it a little bit more closely, it's the same thing all over again. There's not only just one house, there's only one column, and there's only one window, and there's only one street lamp. So it's just repetition and using the indices of the repetition operators to manipulate the inputs of the next repetition operators. So the spacing between the columns of these two buildings is different. That's because each building has an index, and that goes into a random function, and out comes what goes inside the column distance. And also there's like different kinds of roofs or balcony locations and so on, and it gets a bit more complicated, of course, but basically, that's just it. And then we'll have a look at another thing. So this is some object I made. I think it is animated. Yeah, it is. I use this mainly to show off one interesting thing that you can use, because imagine you have this object in your scene, and there's some thing around it. There's an environment, there might be other objects, or this one might be somewhere in the corner, and because you haven't shown it properly yet, but it has to be there. So every time you evaluate any other point in the scene, you have to evaluate the function for this whole complex object, which might be a little bit slow. So the usual thing to do is what I call guard objects, what I call proxy objects. And by that I mean, one moment, there it is. Can't talk about the whole code, but I'll just show you what this does. For each of those gears, I first compute this very rough object, which is very cheap, and only if that outputs a value that is lower than some threshold, I do the rest of the computation. So if you're far away, the individual gear thing looks just like this torus disk thing. But if you come near, then it switches to the detailed implementation. So you could call it level of detail-ish, but the basic idea is just to don't do the computation where you don't need it. And you can nest those as well, so you could put this whole thing in another proxy object and only evaluate it if you're near that. So that really helps a lot for performance if your thing is ALU bound. One problem that we had while coding generally is that the shaders tend to become quite big, because in this case, most of the time it will just compute the very cheap proxy object I just showed, but the code for the more complex rest of the object, it has to be there, and it has to be present on the graphics card, because it won't know when to take that jump or when not. And one problem is that the instruction cache of the graphics card might be flushed all the time, and your shader might become slow just because of the amount of instructions and the amount of code that is actually not executed. So you can sometimes get a speed up by removing a part of code that is never executed. So things like that really can happen. yeah, that might be a problem. Also, an interesting thing is shader compile times. If you code this stuff a lot, your shaders might take longer and longer to compile, and because all the noise functions are so slow and so big, yeah, well, that might be a problem. One solution is, for example, when you're computing the normal, you're evaluating the distance function 6 times. You could, if you do it in a loop, it's just one instance of the function that gets inlined at that point. If you do it explicitly 6 times, it gets inlined 6 times. So your whole big distance function will be effectively pasted in there by the compiler 6 times, so it gets really huge. If you call it by a loop, it's awkward to write, but then it's only 1 time. So it might be worthwhile to experiment with calling similar things if you're calling them multiple times from a loop instead of calling them individually in your thing. All right, do we have some time for questions? Perfect, all right. Questions, please. Seriously? All right.
Hello, I tried this Proxy Objects thing a few years ago, and it actually gave me a worse performance. Why could that be?
Sorry, what was it that you did try?
I had a complex object, and I created a cube, which if it's far away from the cube, I don't evaluate the complex object.
Yeah.
And it gave me worse performance. Why could that be?
I don't know. Normally, this works quite well. It works well if there's a ratio, a big ratio between the complex object, but generally this thing just works. Maybe on really old hardware that was not that good. Like we have like real branching now, and it is okay to use branching if you do similar things in similar parts of the image. But generally it might just have been the old hardware. On new hardware, generally this works. You can do it. Right. More?
Yeah, I was just wondering what your preferred way of doing textured information and things like that is, whether to have that as a separate function and just have one function for distance and one for other information. Yeah, so the applying textures is, we've changed it several times over the last 1.5 years. So we do like procedural materials. We use just 3D materials that we make up. What we do is basically we call the function once after the sphere tracing is done. We call the function once again, but we set a special parameter which says write the material constant somewhere, and then it does just that. But that has the problem that the material evaluation would be inside the function that makes the code big, which is normally not needed. So we so at the moment we do it like this, that we write a struct that we call a material definition. That is very cheap to evaluate, which has an index and a color and the position and a scale and 4 arbitrary parameters that each material can use as it wants. And then that afterwards we look at this material definition struct, and according to the index we switch between the materials. So the scene can have a list of materials with a switch case statement, and one of them is chosen and evaluated, and yeah, I'm over time, I guess. And yeah, so we try to delay that, the material evaluation, and we just keep the values that are absolutely essential for the material and store them for a short time. So that's basically it. Yeah, I guess time's up. So, all right, thank you.